Okay.
Buenos días, bienvenidos a todos. Vamos a celebrar una nueva edición de la Conferencia Santaló. La Conferencia Santaló es uno de los actos académicos más importantes del año de la facultad y, por lo tanto, ya más abre un poco lo que es el año. Nosotros la actividad la hemos empezado antes, pero digamos que oficialmente pues este es un acto que abre este curso. La Conferencia Santaló la organiza la Revista Matemática junto con la facultad y a propuesta siempre de un miembro del comité editorial. Yo quisiera dar las gracias al director de la Revista Matemática, el profesor José María Arrieta, como director y por las gestiones de organizar todo el acto, de colaborar en la organización. También quisiera agradecer al profesor Leandro Pardo, que es quien ha propuesto al conferenciante y el tema y que nos presentará a continuación en unas breves palabras acerca de nuestro invitado. Nuestro invitado es una persona de amplio prestigio en el mundo de la estadística y además está dando temas muy distintos y sobre todo este tema del dióxido de carbono, que es un tema que hoy está muy en la actualidad. Yo quisiera agradecer también a todo el personal de la facultad que ha hecho que esto se haya podido organizar de una manera agradable y a todos ustedes por venir, en especial a todos los estudiantes. Creo que es bueno el que oigamos charlas de investigación para que podamos situar nuestro aprendizaje dentro de este mundo. Y finalmente, only a few words to thank you for accepting this talk. I hope that is a very interesting subject and I hope to enjoy your talk. Thank you very much, Professor Cressie, to accept to give this talk.
Thank you.
Thank you. A continuación, le paso la palabra al director de la Revista Matemática, el profesor José María Arrieta. Por favor, profesor.
Bueno, estimado decano Bru, estimado profesor Leandro Pardo, estimado profesor Cressie, profesores, colegas, amigos y estudiantes. Muchos estudiantes veo en la sala y eso es muy bueno. Ya que hay muchos estudiantes, me voy a dirigir un poco a vosotros, los estudiantes. Es bueno que sepáis que en esta facultad hay una revista, que es la Revista Matemática Complutense, que publica artículos de investigación en matemáticas, cuidadosamente seleccionados por un comité editorial. Lleva funcionando más de 30 años. Se lleva con mucha cabeza, pero también con mucho corazón y con mucho cariño. En la Biblioteca de Matemáticas, ahora cuando salgáis de la conferencia, vais a la Biblioteca de Matemáticas y entrando a la izquierda hay un expositor donde podéis ver la Revista Matemática Complutense. Se me ha olvidado traer un ejemplar, pero es un ejemplar así con la carátula verde. Y las publicaciones en revistas científicas es la forma en que los investigadores comunicamos a otros colegas y a la comunidad científica en general los avances que hacemos cada uno en nuestras áreas. Y en particular en las matemáticas. Y la verdad es que es un privilegio que la Facultad de Matemáticas, la Universidad Complutense, tenga una revista de matemáticas de investigación. Desde sus inicios, allá por el año 87, la revista se tomó en serio su función y ha ido creciendo hasta convertirse, con el esfuerzo de muchísima gente, en un referente de revista de investigación en algunas áreas importantes de la matemática. Últimamente ha tenido muy buenas evaluaciones de calidad en el ranking del Journal Citation Report, que este JCR, Journal Citation Report, recoge las mejores revistas matemáticas de todo el mundo. Recoge aproximadamente 310 y para que sepáis, pues las últimas evaluaciones que ha tenido la revista ha caído en la posición 51, 60, 101. Quiere decir que se ha situado en dentro de las mejores revistas. Es un orgullo para la Facultad de Matemáticas, para la Universidad Complutense, tener una revista de este estilo. Obviamente este éxito no hubiera sido posible sin la labor de muchísima gente que lleva haciendo la labor editorial por mucho tiempo y acompañando a la revista. En particular, los editores jefes, los directores anteriores, Enrique Uterolo, José Luis González Llagona, Enrique Arrondo y Fernando Cobos, y todo un consejo editorial formado por profesores tanto de la facultad como de fuera de la facultad, que son los encargados de decidir y seleccionar estos artículos de una forma concienzuda y científicamente, un trabajo bastante pesado, digamos, ¿no? Yo me gustaría agradecer en particular al comité editorial con el que yo he venido trabajando por ya 8 años, y es José Fernando. Son profesores de la facultad, seguro que muchos os han dado clase, os estarán dando clase, o os darán clase, y es José. Lo digo también para que sepáis que los profesores que os dan clase, además de dar clase, hacen muchas otras cosas afuera y que les lleva mucho tiempo también, ¿eh? Entonces, por ejemplo, José Fernando, Jesús Jaramillo, Narciso Martí Liet, Fuensanta González Montesinos, Vicente Muñoz, Leandro Pardo, David Pérez García, Aníbal Rodríguez Bernal, Alejandro Melle y recientemente Javier Soria se ha unido al equipo, y yo a todos ellos les estoy muy agradecidos por toda la labor que han hecho durante todo este tiempo. Además de esto, la revista cuenta con 35 editores internacionales, no solamente los profesores de la universidad, sino de fuera, que dan un aporte muy importante a la revista. Uno de los cometidos del comité editorial de la revista es organizar esta conferencia, seleccionando a un matemático con renombre internacional, invitarlo a que imparta una conferencia y que luego envíe un artículo a la revista. Eso es importante para que la revista siga su curso, ¿de acuerdo? La elección del conferenciante se hace con sumo cuidado, esmero y rigor científico, y es una de los, como ha dicho el decano, es una de los, digamos, acometidos de la revista, que es muy importante. Esta edición, que ya es la número 18, empezamos en el año 2002 y hemos tenido matemáticos de mucho nombre y de muchas áreas de la matemática. Reconozco que es especial para mí, pues es ya mi última Conferencia Santaló como director de la revista. Ya llevo yo 8 años dirigiendo la revista y en diciembre se acaba de alguna forma el mandato. Es bueno que lo coja gente nueva, sabia nueva, y bueno, es especialmente, digamos, es especial para mí. Agradezco la confianza que ha depositado en mí la Facultad de Matemáticas a la hora de encomendarme la dirección de la revista. De hecho, este agradecimiento es aún mayor, pues han depositado la confianza en alguien que ni siquiera está en la Facultad de Matemáticas. No estoy adscrito a la Facultad de Matemáticas, estoy adscrito a la Facultad de Químicas, pero soy matemático. Estoy seguro y confiado que el nuevo equipo que asuma la dirección de la revista continuará y seguramente mejorará con creces la labor que hemos venido desarrollando. Pido al decanato que le brinde todo el apoyo y confianza que se merece. La revista es muy importante para la facultad y es muy importante para toda la universidad. Y ya por último, simplemente agradeceros a todos vosotros por estar aquí, aguantar este rollo que os he echado, y además agradecer realmente al profesor Cressie que haya aceptado la invitación de venir desde muy lejos, desde Australia, a impartir esta conferencia que seguramente va a ser maravillosa. Muchas gracias.
Tiene la palabra el profesor Leandro Pardo, que se encargará de hacer una breve introducción del invitado y del tema. Muchas gracias.
Well, it's a really pleasure to introduce all of you to Professor Noel Cressie. I know him since many years ago because in 1998 we had a natogram. With that natogram, I had the opportunity to meet him first in Iowa, in Ames, and later in Ohio, in Columbus. And also I had the opportunity to visit Madrid, our department, our faculty, and for this reason, it's not the first time that Professor Noel Cressie gives a talk in our faculty. Since then, we have had frequently contact. We publish in relation with the natogram for paper, and in this moment, my feeling is that Professor Noel Cressie is my friend. But of course, Noel Cressie is not here to be my friend. Professor Noel Cressie studied here because he's one of the most important statisticians in the world. And of course, in spatial statistics, he's the most important statistician. Before coming to the talk, I have seen in Google Scholar the number of sites that have Professor Noel Cressie. Professor Noel Cressie has 43,000 sites, and the number 8 is 72. Then it's very important that number. If he has a book about spatial statistics, that is the most important book in the area. And the book has had some prize because it's an excellent book. I want to say more thing about is fellow of the American Statistical Association, fellow of the Instituto Nacional de Statistics, fellow of the Spatial Econometric Association, elected member of the International Statistical Institute, and so on. Perhaps the last one is last year was elected fellow of the Australian Academy of Science. From my point of view, it's a big honor for our faculty to have Professor Noel Cressie as an invited professor to give the Santaló lecture this academic year. Thank you very much, Professor Noel Cressie, for accepting the invitation of the faculty.
Thank you.
Muchas gracias. Okay, Professor Noel Cressie, we want not to take more time. It's your time. We hope to enjoy your very exciting talk. Thank you very much.
Thank you for coming. The honor is mine, I can assure you. This is a very grand title. I am speaking to a department of mathematics, so I thought I'd start off with some very simple differential equations and then perhaps make them stochastic, and then give you some idea of what we do with stochastic partial differential equations. Okay, this is the very simple PDE. It's in one-dimensional space times time, and it's a homogeneous reaction diffusion PDE. You'll notice that there's nothing stochastic, there's nothing random about this PDE at all. There are different parameters, obviously, diffusion parameters associated with the partial differential equation. And what I've put up there are three different choices of alpha and beta. And I'm going to concentrate on this particular choice, alpha equals 1 and beta equals 20, just because I can use it to demonstrate what it means to make that equation stochastic. So what we're going to do is essentially add a stochastic component here, delta. It's the same PDE, but when there was a non-stochastic component, delta was equal to 0. Okay, and we're going to assume something about the moments of delta and its covariance function. Very simple, in this case, a very simple covariance function that essentially says it's white noise. So this is a simulation from that PDE, and it's represented again by alpha equals 1 and beta equals 20. But the three different components represent the scale, the variance, the standard deviation of that stochastic component delta. And here it's 0.01, here it's 0.1, here it's 1. And you can see that when it's really small, when the variance sigma is 0.01, that it looks very much like the original when delta was equal to 0. And now it starts to diffuse a lot more, and we really cannot see the color that was put in at the top here. The axis, by the way, is time running down vertically, and across is the one-dimensional space. So it's very simple. This plot is sometimes called a Hofmöller plot, and it's used in climatology a lot, and I use it a lot in my research. So the nice thing about that particular stochastic PDE is that it has a covariance function in space and time that's quite easy to compute, and it can be computed in closed form. So I'd like to try to demonstrate what can be done numerically versus what can be done exactly. And the actual PDE can be found as a member of a class of PDEs in a paper by Heine in 1955. That's what the correlation function looks like for this diffusion injection equation. What I have here, what I've shown is along here. You can see I have space, and up here I have time. And you'll notice that the correlation, of course, is 1 down at the origin, and it moves away. So that's just a plot of what the correlation surface looks like for this stochastic partial differential equation. The important thing about any work that we do in applied mathematics and applied statistics is that often just by looking at realizations, it can be misleading. If I showed you these 3 realizations, you might think that they were generated by different partial differential equations. But in fact, they're just 3 different random choices of the stochastic component delta. And so what we do in statistics, of course, is that we do some averaging and we compute summary statistics. And in this case, we can compute the covariance function. I would urge you that when in your applied work, it would be good not to be too taken in by one particular realization, because in fact you have replication, and sometimes you can see they don't actually look identical, and they shouldn't because of the stochastic component. So the next point that I want to make is that often in a computer we don't have continuous time, so we want to make discrete approximations. We don't have continuous space either, so we pixelate the area of interest. So we have pixels both in space and time, and they're finite. And it's possible to approximate that differential equation here by a difference equation. So that's all I'm going to do. I'm just going to take a difference equation and approximate it. When a computer solves that partial differential equation, that's exactly what it does. It looks at pixelation and it approximates it. But because I'm a statistician, I then start to put things on the left-hand side and on the right-hand side. And I'm very interested in what happens at time t and how it relates to what happens at time, well here, t plus 1 and time t. I've written delta t because it's a bit more general, but let's think about choosing delta t so it's 1 unit of time. There are actually conditions that need to be satisfied to make sure that this particular approximation for differencing approximates the differential equation. So we're careful to do that. The cool thing is, and it is cool, is that when you write down that matrix M, let me just go back and remind you of what that matrix M is. Okay, it's sometimes called a transition matrix. In this, it's Markov in structure, so there's a transition that takes us from yt to yt plus delta t. That matrix M has a lot of structure associated with it. Okay. And in fact, the theta which I write down is related to the alpha and the beta, which are the diffusion quantities in that injection diffusion equation, in the following way. So I can go from what's down diagonal and what's down the off diagonal, and relate it to what the alpha and beta are. Then there's a bunch of zeros, and those zeros are really important because as statisticians, we want to make sure that we don't over-parameterize the problem. Now, often in spatial statistics, people just take M, that matrix, that transition matrix, and they say, I'll estimate M. But when I have 1,000,000 pixels, M is 1,000,000 by 1,000,000, and I then have over-parameterized the problem. However, if I think that I have a differential equation driving the problem, a partial differential equation, M has some very simple structure, and it's zeros everywhere. And now I'm in a domain where I can actually do estimation. Just to show you that I get answers which are reasonable, what I've done is I've computed in red, in blue, I've computed the exact partial differential equation's covariance function, stochastic partial differential equation, and then the red dots indicate an estimate that I've got. And you can see that the pixelization does very little to the true covariance function, which we would hope, but it's more just a demonstration. The solid blue line is the true. The red dots are got from the difference equation. So what I'm trying to demonstrate here is through this partial differential equation, I have a manifestation of the first law of geography, which nearby things tend to be alike than things that are far apart. And that's what has driven my research in the last 25 years, is this so-called law of geography. Of course, it's not a law. It's just an idea. It's a philosophy. It's a way we approach the subject. The cool thing about having a difference equation, and you'll see in a minute, well, maybe in 30 minutes, but you'll see that instead of trying to solve the differential equation, all we need to do to do this statistical analysis I'm going to do is compute with it. We approximate it by a difference equation, and then we use something called Bayes' theorem to actually do the computing. So the approximation is simply, sorry, I'm having a little trouble, the approximation is simply writing yt in terms of yt minus 1 with this transition matrix M. But now, since I don't really have to solve the PDE, I have to work with it, I could maybe just start modeling MT. I could change MT. Doesn't have to be the same for all T. And what I've done here is I've chosen, you can see, I've chosen some function. I just made up a function, which I multiply by M, and that's a function of time. So all I'm doing is just getting rid of all that stationarity, getting rid of all the homogeneity, and I'm putting in something which might actually be quite realistic. And then I ask the question, can I compute with it? And I can. And here's the sort of images that we get. The covariance functions won't be homogeneous and stationary anymore, but we can compute with it. And so it frees up the study of certain problems, not every problem, but let's just say spatio-temporal dynamical statistics. It frees us up from certain assumptions, because what we want to do is not necessarily solve a PDE, we just want to compute with it, and using Bayes' theorem. And this particular approximation using a difference equation, you'll see, will allow us to compute with it in really big problems, okay? So what I've chosen is a very small problem, one-dimensional space, time, and I've specialised in a particular PDE where I can solve it exactly and where I can compute with it, and I've compared the two, and I show that what I compute with is approximately equal to the exact solution. It's not a theorem. It's more of an indication that when you compute with these things, you're getting an answer which is close to what you should get. All right, so now I want to move on to atmospheric problems, remote sensing, carbon dioxide, that type of thing. And I'd like to point out to you that this is what our Earth looked like 3.6 million years ago. Why did I choose 3.6 million years ago? Well, Homo sapiens were not on the Earth 3.6 million years ago. That's a picture. Wasn't taken by a human. It's an imagination of what the temperature was like, what the Earth looked like. There were no humans walking on the Earth 3.6 million years ago. The last time the Earth reached 400 parts per million carbon dioxide, the last time was 3.6 million years ago. For 3.6 million years, our Earth always had a carbon dioxide content below 400 parts per million. We reached 400 parts per million 2 years ago, actually 3 years ago. And we're heading north. So this is an actual representation of two different monitoring stations. One is in Hawaii, and the other one is in Tasmania off the coast of Australia. One is in the northern hemisphere and one is in the southern hemisphere, and they're half a world apart. They're both telling the same message. The graph on the left is global carbon dioxide, and compare it to the graph on the right, which is from two individual stations, and the message is the same. Our carbon dioxide is increasing. It is a greenhouse gas, and as it increases, it will lead to climate change. It is leading to climate change. This represents a network of stations which looks up into the atmosphere at the sun, and it counts actually the number of carbon dioxide molecules in a column going up through the atmosphere. It's a very accurate reading. Unfortunately, there are only 25 stations in the world, and they don't move. This is a very compute-intensive station. It has to be stationary, it has to be there all the time, and it is monitored and calibrated extremely carefully because it represents what's called ground truth. Okay? And I would like to point out when this gets going. Well, I will point out, you see Wollongong over here? Okay. Department of Chemistry has one of these instruments on their roof, about 100 metres from my office. And I work closely with the Department of Chemistry, and we work on some statistics for that particular instrument. This network is called TCON, or the Total Carbon Column Observing Network. Okay, so let me now just sort of try to express this mathematically. Let's think about X being a four-dimensional spatiotemporal process. So I have little x is longitude, little y is latitude, h is geopotential height or altitude, but it's measured in geopotential height, which is air pressure essentially, and t is time, 4 dimensions. And I'm interested in that whole 4-dimensional process. So remember, I had a partial differential equation with one spatial location and time. Now I have partial differential equations with three spatial locations: longitude, latitude, geopotential height, and time. And I'm particularly interested in what happens at Earth's surface, because that's where carbon dioxide comes out of the Earth and it goes into the Earth. Carbon is the fourth most abundant element in the universe. Earth has as much carbon as it's ever going to have. It's constant. If we take carbon out of the Earth and burn it, it goes into the atmosphere and it stays there for a while. And then it goes back into the oceans and it's absorbed by photosynthesis by the plants. So there's something called a carbon cycle. We're very interested in the carbon cycle. This idea of sources and sinks in the carbon cycle is fundamental to understanding climate change. Because on this planet, we will always have this planet. It's not clear that we will have a planet that humans can live on, but we will have it. There will be a planet. We're not destroying the planet. Perhaps we're destroying our environment. And that's what we're trying to determine. If I can work out where the sources are and the sinks are, I can minimize the sources and I can maximize the sinks. So this is a problem that our whole planet has to solve. You've probably heard of COP21, which was an agreement signed in Paris in 2015. There is an attempt there to stop carbon dioxide coming out into the atmosphere. It doesn't say anything about sinks, more about sources. However, every country, 163 countries, signed on to the COP21 agreement, and because there's an attempt to keep climate temperature increase below 2 degrees Celsius. And the belief is that we can just keep reducing our carbon dioxide little by little. By 2050, we would have solved the problem of keeping the climate below 2 degrees increase. It's not working. It's not working because we're not keeping just those limits, and because the United States will withdraw from the treaty next year. They've given notice that they will withdraw, and formally they will withdraw from the treaty next year. So different countries have different commitments depending on whether they're a developing country or a developed country. The developed countries like Australia and the United States agreed to reduce their carbon dioxide equivalents to between 24 and 26% by 2030. It's not very far away, but all I'm trying to point out to you is that we're very worried about this thing called X here, carbon dioxide in the atmosphere, and we're even more worried about this thing called XF, which is the rate of change of carbon dioxide at the Earth's surface, because SXY is the geopotential height of the Earth's surface. That is an equation which we are trying to get at, and it's a differential equation. It's actually stochastic because X, the true state of the atmosphere, is unknown, and we model probabilistically and stochastically. And the goal is to infer the flux, XF, from the data that we have. All right. Okay. So just want to do a little bit of showmanship. Just put on my uniform here. Okay. I'm a member of the science team of National Aeronautic Space Administration, NASA, of this particular instrument. It's the first instrument that NASA has launched that principally looks at carbon dioxide in the atmosphere. And it successfully launched about 4 years ago. That's it going up. I was there. Let's see, where am I? I'm down here somewhere. Can't you see me? Yeah, right, good. I couldn't see me either because it was foggy and we didn't even see the rocket take off. We were at the launch, but all we heard was and it's gone. But that's another story. But it did launch successfully. Now, the problem is that we don't observe fluxes. We observe columns. The satellite's flying over and it's looking down at the Earth. It's looking through a column. And that is the reason why this is called X sub C, for column. What we want to infer is X sub F for flux. And flux is the rate of change. It's a differential equation. Unfortunately, X sub C is the opposite. It's an integral, or a differential. And it's quite different. It's observing parts of that whole four-dimensional field. So we want to measure X sub C, and we do. And as statisticians, we're careful to make sure that we don't mix up the true column value with the measured column value. We do write an equation that says Y sub C, the data, equals X sub C, the underlying state, which is we're trying to observe, but we don't observe everywhere, plus this thing that you probably learned in undergrad, this thing called epsilon, right? You've all heard of epsilon. So in analysis, epsilon tends to 0, but in statistics, it sits there, it does not tend to 0, and it has a variance associated with it, okay? And we usually call it epsilon. Sometimes that measured quantity is written as X sub CO2. I think this is a physicist wants a different symbol, and X here means integral. I don't know why, but it means integral. And so if you're measuring methane, you have X sub CH4 for methane. So this sometimes is called XCO2 or total column carbon. All right, so this is what I do. I put on my uniform. Yeah. I just want to point out that this is that graph that we showed you of Tasmania. There's Tasmania, and it's being measured. It's measuring carbon dioxide. This is Hawaii, and those two places are half a world apart, and they're telling us the same thing: carbon dioxide's going up. But this instrument, this rocket, this satellite, tells us that carbon dioxide is in different. Sometimes it's red, sometimes it's blue, sometimes it's green, which is indicating that actually carbon dioxide is not homogeneous. On average, when you measure it over a month or over a year, yes, you get an average value. But because we're interested in the sources and the sinks, we have to know whether it's red, where it's green, where it's blue, where it's high, where it's low. And there are some things that we do know, generally speaking. Okay. This is the Northern Hemisphere winter. Okay. And you can see it's winter because we don't get any measurements over the North Pole. Why? Well, because the instrument's passive. It requires reflected sunlight. And in the winter, there's not much sunlight, and so we don't get any readings. But it's not exactly hot or balmy over Antarctica, but we do get readings in the Southern Hemisphere close to the poles. So that's winter, 1st of January 2017, for example. And that's summer. And so you can see that we quite a lot of readings up here, but not many over the poles. So we have a problem. The instrument gives us quite good coverage, but it's different in different times of the year. And also, I'm not doing that, I don't think, so that's all right. But you'll notice here that we get almost nothing. And then look at this stuff here. What's causing this? Well, it's clouds. It's a monsoon season. And those clouds actually stop us looking at the Earth's surface and finding out how much carbon dioxide is in the column. So the point is, this is a hard problem, and data are really messy, and there are a lot of them. There's about 100,000 data points here. It doesn't look that way because I've done a lot of overstriking, but you can see the data are incomplete, and they're messy, and it's really hard to deal with. So what we do is do some smoothing and gap filling of the data. And this is an example. I'm not going to show you it all. You have to come tomorrow to see more of this, right? I'm giving a technical talk tomorrow on how we do this, spatiotemporal kriging. But it represents our way of filling in the gaps. And you can see we're reluctant to go out to the poles, but we're actually able to do some filling in and smoothing. And we end up doing what's called standard error calculations. You might call them error bars, undergrads, right? Plus or minus twice the standard error, all that stuff that you're being taught, good stuff. And we use it all the time here in the rocket science world. Now, I mentioned that I'm going to use Bayes' rule to compute with the partial differential equation, but not to solve it. But I need to show you what Bayes' rule is. First of all, you don't have to be a Bayesian to use Bayes' rule. There's nothing Bayesian about this. Nobody's putting a prior on parameters. What I am doing, though, is I'm recognizing that the state of the atmosphere is unknown. I recognize that it perhaps, and I know the mean and the covariance functions of the state of the atmosphere, but the actual state is unknown. And so I put a distribution on it. That's what we do as statisticians. We put a probability distribution on X, which is the true state of the atmosphere. Then we put a probability distribution on Y, which is the measured state of the atmosphere. They would be what the satellite's measuring. X here would be that full four-dimensional process of carbon dioxide in the atmosphere. And we want to infer some function of X, which I call X sub F. Okay? Bayes' rule comes to the rescue. And basically, what we want to do is infer that function of X, or X itself, that four-dimensional state of the atmosphere, given the data Y, which would be these 100,000 observations a day, 365 days a year for the last 4 years. There's a lot of data. And we would now then use Bayes' rule to get it. And Bayes' rule says I need to know what the conditional distribution of the data is given the true state of the atmosphere. And that's not too bad, actually, because that's just the measurement process. That's all I need. That's epsilon. All I'm doing is saying, what are the properties of epsilon? Then I need to know this guy. Well, that's a bit harder. That's sometimes called the process model. And that's where the physics comes in and the chemistry. By the way, the work we're doing on this is joint with the Department of Atmospheric Chemistry. It's the Department of Chemistry, and they have a Centre of Atmospheric Chemistry, CAC. And so we're doing that. So Bayes' rule then says, even if I can't get that full posterior, sometimes called a posterior or predictive distribution, I surely would like to know what the posterior mean is and the posterior variance. So statisticians go, give me the big distribution. And you go, well, I'm not sure if I can. And you say, okay, I'll settle for the mean and the variance, at least the first two moments, and the covariance, because the variance of a vector obviously involves the covariances as well. So I'll take them all. I'll take the full distribution if I can. but at least I'll get the first 2 moments. Now, it turns out our method will get the full distribution, but I'm just going to show you the first 2 moments of that posterior distribution. So can we make this work for millions of observations, hundreds of thousands of pixels, which I've discretized onto Earth's surface, and I need to make some inference about some differential component called the flux? Can we make it work? Well, in principle, you can. In practice, it requires a little bit of effort or a lot of effort, and it's quite hard. You need to be able to build this. This is where a lot of the work goes, right? That's the distribution of the state. And that's where the science comes in. And currently, these sources, fires, respiration, fossil fuels, fresh water, outgassing, volcanism, add to that cement factories, you know, and automobiles, and that's the fossil fuel part. And there are models, actually, where people do this, what's called bottom-up estimation of what we do to our planet, what we do in terms of the carbon dioxide sources and sinks. And the respiration part is the sink, where we have photosynthesis, and we think of the Amazon jungle, and we think of, you know, the jungles in equatorial Africa, hopefully being the lungs of the earth, you know, taking the carbon dioxide out, and then when the leaves start to decay, carbon dioxide comes back in again. So they're the lungs of the earth. And what are we doing as humans? The equivalent of smoking lots of cigarettes, right? We're pumping out carbon dioxide into the atmosphere at a rate which the planet knows it cannot absorb, and hence we assigned the COP21 Paris Agreement. There's an attempt to, in a sense, sort of go off smoking, stop all this carbon dioxide going out. So we know we need to do it, and we need to be careful about how we do it, and then we need to measure that it's making a difference. So that's the sort of work that I'm doing. All right, so this it represents a network, okay? There's arrows associated with the network, and it's what drives the so-called differential equation, the one I said I needed to compute with, but I didn't need to solve. So essentially what I have here, there we go, it's coming. What I have here are the data in purple, okay? What I have here is the underlying state. X sub C are the columns, remember that? But I don't want the columns, I want the fluxes. And the fluxes are related to the columns through a difference equation. Okay, so sort of getting a bit away from differential equations and thinking about difference equations. And here's the difference equation. Here's how the column relates to the fluxes. That's the probability of X. That's what drives this model. And you might say, how are those transition matrices that take us from fluxes to columns, how do they happen? Well, physically, we know how that happens. Okay, I'm a molecule of carbon dioxide. I pop my head out of the soil and I go, okay, where do I go? And then the wind comes along and takes me over here. And I say, oh, it's nice over here. But then another storm comes and takes me over here. So that carbon dioxide molecule is transported by the weather, by the pressure. You know, when you look at the weather map, the weather guy says we have a high pressure here, we have a low pressure here, and the winds are coming here. And it's moving the air molecules. But this large fraction of the air molecules is carbon dioxide. It's also oxygen, and they're in a very strong ratio with each other. So when we have storms, we actually have carbon dioxide storms, right? Because the carbon dioxide molecules are moving around with the weather. So what this represents, these H's, they represent transport or weather. And in order to see what H is, the transport, we use a lot of physics. We use physical models and chemical models. There's a model called GeosChem, which some of you might have heard of, where we actually run the weather at 2-hourly intervals. And we run the weather and we see what happens to the molecules in the atmosphere, every molecule. But we obviously accumulate the molecules and we end up computing H of T. And you'll notice that H depends on T and T. And here T and T minus 1. So it depends on the season, it depends on the weather at the time. I wrote out that equation, difference equation, with M sub T. Do you remember that? I had M, and then I said, oh, what about if I'd had M sub T? Well, I did that on purpose because over here I have H sub T, T minus 1, T minus 2. So what happens when a molecule pokes its head out of the atmosphere and starts moving around? It takes about 3 months for that molecule to sort of settle in and become part of that background 400 parts per million. Okay, then there's a background, and in the meantime, new molecules have come out and some have been absorbed. So this particular time here goes back to T minus 2. T minus 1, T minus 2, by 3 months it's gone. So we stop the difference equation at T minus 2. This is the flux. That's those little molecules poking their head out, and then it's moved by transport. This is basically how one flux moves to another, and that's important too, because it's an evolution of the fluxes. So just using very, very large matrices, I'm able to write down all these difference equations. And I have the measurement equation at the top, and I won't go into what all those terms are, it's not important. The important part are the difference equations and the way the fluxes evolve. So I have a very dynamic structure, both in terms of transport, in terms of the fluxes themselves, and the seasonality of the fluxes. My goal is to infer this is a vector, by the way. This is a 100,000 dimensional vector. For every pixel on the Earth's surface, I'd like to infer those fluxes. These slides really just show, we wanted to be sure that we were getting the right answer. I could put anything into a computer and come up with an answer. I'd say, oh, looks good. Looks good. That's what we call the LG metric, the looks good metric, right? Beware of the looks good metric, right? So what we wanted to do was to build what's called an OSSI, an observing system simulation experiment. And that OSSI has my satellite moving around in the computer. And it is looking at Earth's surface and absorbing parts of the Earth's surface, but it's not really the Earth's surface, it's the virtual world. But it's a world we can control. And because we have this method, this model called GeosChem, it will tell us exactly what the atmosphere looks like, what the Earth's surface looks like at that particular time, at that particular location. It's very, very accurate. And we use ECMWF, which is European weather forecasting databases as well. Lots of data, big data for sure, but not impossible to come up with what we see. Now, remember I said we're statisticians. There we go. I think we'll get it now. Here we go. What we want to do is basically look at the truth, because remember, because it's a simulation, I know the truth. And I want to look at the estimates that I get, given the Aussie data, plus or minus the standard errors, or plus or minus twice the standard errors. And I want to compare it to this true value, which I have artificially constructed. Okay, so let's see how we do. In order to get some sense out of this, you have to aggregate at certain points. I want to emphasize that the analysis was done at a very fine resolution, but we aggregated to these 22 regions. The first 11 represent land, and the last 11 represent ocean. And it's important to remember the first are land and the last are ocean, because we get different answers. Okay, so this is the perfect world. These are my 22 regions, going Transcom 22. The green here, see if this works, there we go. The green here are land. The blue represents ocean. It's not bad, right? Red is the truth. Then I have a darker grey, which is plus or minus 1 standard error, and I have a lighter grey, which is plus or minus 2 standard errors. And, you know, stuff happens here, that's over the ocean. Can you notice that the standard errors are a lot smaller here over land than they are over ocean? You see that? Well, that's actually what happens in practice. And people who are working on this with us in NASA are aware that the oceans are problematic. It's just, it comes with the territory. So now I'm going to do something quite shocking. I'm going to use a model for analysis which is different from the model that I built the Aussie from. Now, quite shocking, because why would I do that? I'm purposely using the wrong model. And the answer is because in practice, that's what we always do. We use the wrong model. We have something called, here, we have something called a true model, which is in the Aussie. And then there's something we call a working model, which isn't exactly the true model, something a little bit off. And what I did, and you'll see, is I left out a coefficient. I'll just go back very quickly. It turns out this beta here, this linear term, is really important. It's part of the measurement process. And unless you get that right, all hell breaks loose. And so what I did is I basically rolled back history, and I left out a term which is absolutely essential. But for 2 years, the flux inversion team couldn't work out why their analysis was having trouble. And this Aussie shows us why. So I'm going to leave out one of those terms. And I want to show you what happens. There is no way that inference makes any sense over the oceans. It's not just a problem of precision anymore, it's a problem of accuracy. And this term called S31 represents aerosols in the upper atmosphere. And it had been left out for 2 years in the analysis. So I put it in, we did the Aussie, and then I left it out. And it explains why there was a lot of problems. So just want to point out that the number of data that we used here is close to 3 million. No, more than that. It's about 2 years worth, probably 100,000 a day. It's very close to about 100 million data points. And we ingest it and we use Bayes' theorem in order to come up with these answers. So what is happening now with my group, and we have a grant from the Australian Research Council to do this, it was now replacing the Aussie with the real data, and we're in the process of experimentation. I wish I could show it to you, but it's not ready yet. Our postdoc has just arrived last week, and we're about to gear up. So let me move back now to that idea of spatiotemporal statistics and what's important. I've shown you that the important part, a big important part, is the dynamics and doing the difference equation. But those of you who would like to get involved in this spatiotemporal statistics should really take note of a number of topics which I would call under-researched. So the point I'm trying to make is there are many, many things which you could do in this area. And then a very small plug. If any of this interested you at all, there is a book, and the book is free. Okay, you can take a photo of that and download the book. It's absolutely free. It's not that it's cheap, it's free. You understand the difference. It's also possible to purchase the book from the publisher, but we made a deal with the publisher we own the copyright, so you can get it yourself. So having said that, I'll finish. Thank you very much for your attention. I'm happy to take questions.
Thank you very much, Professor Noel Cressie, for the nice talk. And now there is some question for Professor Noel Cressie.
Thank you, Professor. A very nice talk, a very interesting subject. But I have not understood what is the role of the atmospheric dynamics in all this, because you are using a white noise or a Gaussian noise, but this type of noise is able to simulate the dynamics of the atmosphere. Right. Thank you.
So you're welcome. Actually, it's a great question, because there was one particular term I did not emphasize, and that is that's what I work on actually a lot, is this term S eta t. And you'll notice that eta t depends on time. So while the physics goes here, but whatever it is that the physics can't handle is handled by this term, S eta t. And this is the place which enables us to do the dimension reduction, that enables us to handle 100 million data points. This eta t is only dimension about 400. And all the activity in space is handled by what's called the basis functions in that matrix S. So it's a great question, and I didn't address it. I was more addressing the physics. But S eta t is where the spatiotemporal dynamics is. And that is, so the PDE part becomes a difference equation here. But remember, in that PDE, there was this error term delta, and I assumed it was simple. Actually, in everything we do is we assume it's complicated, but of reduced dimension, and we can make inference on that. Thank you for the question.
More question? Well, I have a question. In the spatiotemporal statistic modeling, there are two approaches. One approach, a dynamic approach, and a descriptive approach.
Is it on? Yeah. It's on. Good.
I repeat the question. In the spatial-temporal statistical modeling, there are two approaches. One approach, a dynamic approach, and a descriptive approach. My question is the following. What are the advantages of the two approaches, one approach, one other approach?
Okay, thanks, Leandro. I guess it's sort of summarized here. Remember I said that we had an equation Right. We have this very simple differential equation, which I'm now going to discretize with a difference equation, and then I'm going to capture through this difference equation. And I demonstrated that you can get very close to what the true solution is for the partial differential equation. What I have in here, and why do we do PDEs, is because we want to understand the dynamics and we want to actually forecast into the future. If we do just the descriptive approach, then we're stuck just with the covariance. That's all we have, just these covariance functions. And we don't understand the dynamics. We don't understand the alphas and the betas, and the inference on those becomes quite difficult. So for a long time in spatiotemporal statistics, and I worked in this area, we were coming up with spatiotemporal covariance functions. And we'd say, oh, I've got a spatiotemporal covariance function. It's positive definite. End of story. I go on to my next PDE. But it's not very helpful to do forecasting or to understand why these fluxes are occurring where they're occurring. So it really comes from the interpretation and the power of forecasting. Thank you for the question. Yeah.
More question?
Yes, one at the back. Hello. Sorry? Yes, if you speak loudly, I'll repeat the question. Oh, here comes a microphone.
So I was wondering if you could tell us a bit about how the satellite works.
Yeah.
That one you sent up, because you said like a little bit about how it processes the columns, but you didn't get much into it.
No, I didn't.
Thank you.
So thank you for the question, because I love this stuff. I'm not a rocket scientist, but I would like to be. So this is a satellite. It's kind of flying around. Actually, somebody drew it. It's an artist impression. And this is it going up. There's a few important things here. And look, here's the data. So here's what happens. We're trying to measure total carbon dioxide, but we don't get a direct measurement. It's not like that satellite has a thermometer or something hanging off it and it's going dragging it along. What you see is actually photon counts. Those photon counts come in certain very small parts of the electromagnetic spectrum. And this particular instrument has it has a camera actually, 700 kilometers high. And the amazing thing is that the accuracy needed is plus or minus 1 part per million out of 400 parts per million. So these are very, very accurate instruments, and it's the satellite's flying over and it's taking pictures every fraction of a second. And the sort of pictures it's taking that's coming back are energies or radiances. And they're essentially photon counts that in a region of the near infrared spectrum, you'll get something called the strong CO2 band, which tells you a lot about carbon dioxide, but there's another place in that electromagnetic spectrum is also sensitive to carbon dioxide called the weak CO2 band, and they're different. And in those bands, what will happen is that if the reflected sunlight hits some of those carbon dioxide molecules, energy is absorbed. When the energy is absorbed, it reaches the satellite, and there's a dip, and it's not a very big dip because the energy is absorbed. Sorry, it is a big dip because the energy is absorbed. So when you actually look at the data, not this data because this data has already been processed, but when you look at the data, the spectral density of the data, it's looking like this. For one particular snapshot. And then there are 100,000 of those snapshots in any one day. So to determine this one, called the XCO2, a whole new set of equations have to be solved, and it's called an ill-posed inverse problem. Now, I think mathematicians here know about ill-posed inverse problems. I've certainly been reading enough about it so that I can be dangerous and say something about it. And the ill-posed inverse problem is essentially used by Bayes' theorem. So there's two uses of Bayes' theorem. One is to get this, and then the other use of Bayes' theorem is to do the flux inversion. So it's a great question, and there's so much energy put into just one of these, just one, and then you need to get 100,000 of them. So every time satellite flies over and is taking pictures, the data is downloaded on every orbit to a particular station that NASA has in Fairbanks, Alaska. Those data are then sent to the JPL in Pasadena, California, and then I start working with them along with other people. So the data I get, that I've been working with, are these things that look like this, and they turn into this XCO2 value using Bayes' theorem. There's a lot of work going into one of those pixels, and there's a lot of those pixels, and then there's a lot of work going into coming up with the flux inversion. It's great. It's great. You could spend a lifetime on this, but it really is. It's a great statistics problem, and I think we're making a contribution. Couple. Oh, there were a couple over there, actually. Yeah.
Hi. Just about the kind of perfect model work that you've been doing.
True model, working model, was that?
Yes. What kind of model is it? It's just atmosphere model? It's coupled? Is you're using boundary conditions for that? Or
yeah, so to get the H's, we spin up. We basically start on a very benign Earth, and then we add the winds and the weather and the transport, and gradually spin that up. And of course, we don't look at what happens in the initial boundary conditions. We sort of wait until they settle down, and that enables us to get H at T, H, T minus 1. So there's involves the running of this GeoS-Chem model, where the spin up is done to get the atmospheric transport H, T minus 1, T minus 2, etc. And that's handled by our atmospheric chemistry. We have somebody at the University of Wollongong who is in the GeoS-Chem team, fortunately. We could not do this by ourselves. Statisticians, you know, we have our strengths, and this is a statistics problem, but that transport is something that is really hard, and we need help. And in fact, so I have built a team now with a lot of atmospheric chemists and statisticians and mathematicians and various things to try and solve this problem. So does that help? And I can help some more if
yes. And just to follow up,
yes.
I don't know if I didn't get it right, but like your representation of ocean, let's say carbon fluxes were not spot on as with land, and do you have any clue on?
Yes. So why? The reason why is this term here, this ATB. You'll notice it's in the measurement equation. It's not over here in the state. It's not working. Oh, there it goes. It's here in the measurement equation. YC is the measure, and it has been discovered empirically empirically that this satellite, which cost $1 billion, by the way, $1 billion, because the first satellite failed, $500 million. Next satellite worked, fortunately, $500 million. So $1 billion to get all of this. It was discovered empirically that the measurements of ocean were not as carefully, how can I put this? Measurement oceans were not as precise or accurate as the measurements on land. And there's part of a reason why that is. The ocean is dark. And when the satellite looks down at the ocean, it doesn't see anything but black. So there's something about this satellite, it's beautiful actually. What the satellite does is it rotates the camera and it looks at the angle of the sun that hits the ocean and comes back to the satellite. It's called glint. And it looks for a glint spot on the ocean. It can do that on the land too. So looking straight down is called nadir, N-A-D-I-R. And then the satellite can sort of start looking around, right? Where's the glint spot? And you get a glint spot. For the ocean, nadir doesn't work. You get no data at all. But it will look for a glint spot and you get data. It will do it for land. You get both nadir and glint. There's something about the measurement process for the ocean which we know is messed up. And the way to handle it is to put in this AT beta. And what I did was purposely left out one of the components AT. I put beta equal to 0. I knew it wasn't going to work. I just needed to know how badly it wasn't going to work. So there's a lot of work now being put into, in a sense, doing a better job with AT beta. So you never, ever get that awful, picture of what's happening over the oceans. The land is stable, and I think it's because of the use of the glint spot over the oceans that's causing the measurement. So it's partly empirical. If we knew physically why, I think physicists would come up with a perfect explanation over here, and then everything would be cool. But in fact, whatever adjustment is made here, it's drifting. So a term in here with a particular value of beta is good for 2017, but it is not good for 2018. We know that. So there's not enough known about the physics, and the only way to handle it currently is statistically through this AT beta. Okay.
Thank you.
There's another question?
Right, so basically I have two questions.
Yes.
First one would be, how do you get, very similar measurements of CO2 content in the atmosphere when there's obviously a latitudinal dependency in the distribution of CO2 in your measurements?
So let me address that. There's certainly latitudinal dependence, tends to sort of go up, not always perfectly, depends on season, but it tends to increase with atmosphere. And in fact, when you look at, maybe I could bring up the fixed rank kriging thing that I did somewhere back here. Yeah. This tendency to have high values in the northern hemisphere is actually pervasive. It happens in all seasons, but it's just less so in some seasons. So that what's been observed is automatically accounted for in those equations, because remember the H is got by transport, and it just has a spin up that enables us to account for whatever it is physically going on. So that latitudinal dependence is well known. Most of the land is in the northern hemisphere, and much of the oceans are in the southern hemisphere. If I wanted to do a really simple model, just a regression model, and I've done this, and not a physics model, I would use latitude as a regressor for sure. And in fact, we're planning to do something like that to compare this physics model. Yep. So that's the first question.
Okay,
I think it's taken into account by the transport model.
Okay.
Yep.
And the second one is, well, essentially what you do is you somehow estimate the surface CO2 fluxes from a vertical integral of your observations.
Correct.
And when you run your atmospheric simulation with the weather model and you estimate or you trace back the CO2 particles, basically, wouldn't it be important to know about the vertical distribution of the CO2 particles in your column that you measure?
Yes. So the vertical distribution is estimated by the satellite.
Okay, that's possible.
But very badly. Because you can imagine it's just looking down. There's some physics that goes into it. So there is some vertical information, but very badly.
Well, thank you very much, Noel, for
Oh,
your nice talk. It has been very, very interesting. You can see that many people have questions for you. We're very grateful to you.
Thank you for coming, everyone. That's great. Thank you.
Únicamente recordaros que mañana el profesor Noel Cressie dará una conferencia al Departamento de Estadística a las 12:30. Seminario Sisto Ríos, una conferencia evidentemente completamente distinta a esta conferencia. No se repetirá. Os animo a que podáis asistir mañana a la conferencia en el departamento. Muchas gracias.